Okay, should we begin?
Yes, ma'am.
Okay. Good evening. Welcome to our new series, that is intensive revision series. So in this series, which will be for 45 days, we'll be having an intensive revision of all the important topics, rapid revision of all frequently asked questions and high yield topics, so that you can benefit from it in your university exams as well as for your NEET PGs and FMG exams. So here for today's class, I'm going to be taking enzymes. So we have basically, this series is based on previously asked questions and other high yield questions. So just like in exams, you've been frequently asked about enzyme classification. So that is very important, had been even asked in 2013 and 2014. And the various factors influencing enzyme activity. This is also another very important topic and has already been asked in 2006 and 2016. Then you have short essay questions. Again, there also you get asked about enzyme classification. And it has been asked multiple times, as you can see, in the year 21, 18, 20, 2002, 2011, 12. Okay, so this is a very important topic, that is enzyme classification. Then enzyme inhibition is another very important topic, has been asked in 2007 and 2020. So the various types of enzyme inhibitors, competitive inhibition, non-competitive inhibition, uncompetitive inhibition, and all that, that is very important. Then isoenzymes, diagnostic importance of enzymes and therapeutic enzymes. This is another very important topic, has been asked multiple times, 5 times you can see in a row. Then in short questions, you have KM, another very important diagnostic tool and very frequently asked. You can see the number of times it has been asked, like 6 times it has been repeatedly asked. So KM is a very important topic. Then again, inhibition, zymogens, and then your diagnostic enzymes. So overall in enzymes, the kinetics, the inhibition, the classification, and isoenzymes. These are the important topic. And when I say this, I think the entire of enzymes in itself, the chapter is covered. Okay, so for today's lecture, we'll be taking enzymes under these headings, and these, as you can see, have been asked multiple number of times. Okay, then introducing you to the Auricle. So why choose Auricle? Why Auricle above all? So here at Auricle, we provide you with recorded classes, live classes, practical sessions. This is something very unique, which you will not be finding anywhere, okay? Then exam modules and hardbook sets. So in recorded lectures, you have the facility of flexible learning. You are able to assess the lectures as per your convenience. Okay, there's expert instruction from the faculty. There's convenient revision, okay, from the faculty. Then you have the live classes. In the live classes, there's in-depth coverage of all the topics. There is interactive learning. So it is a two-way session where you can, even in the comments while we taking classes, you can ask questions to the respective educators. Then we have express exam modules, which will help you to complete the syllabus in 20 hours, covering it effectively and comprehensively. Then apart from that, we also have doubt clearing sessions. Okay, so there's personalized attention given to every student. So if there's anything that you are not able to understand, or any essential topics or any tips that you want to have, so there are personalized sessions for that. Then this is something very unique, that we also provide with practical sessions. Okay, so you get to have hand-on experience with everything. Like there's expert guidance from the faculty. Then we have a highly updated and effective question bank, so that you can practice whatever you've learned. So we have 3 levels of question banks: the beginner level going up to the expert level, which is going to be very beneficial for your prof exams or the NEET PGs and the FMGs. Then we've recently introduced our hard copy note sets. So we are having these booklets, these modules, where you get the notes in printed format. So if you want to get them, please feel free to get a package where you have all the 3 subjects covered, that is anatomy, physiology, and biochemistry. Apart from that, there's also a practical book. So this, I think, the booklets are very useful. The notes are very comprehensive, very precise, bulleted out, everything concise. You don't have to like search for the material that you require from the different standard books. We've already done that job for you. So in a very precise format, everything exactly how it's required, what you're supposed to write and know, everything put together, not missing out any point in these booklets. Okay. Then at Oracle, we have three different subscription plans. That is the basic, which comes for 1,999, followed by the standard plan, which comes for 34,999, and the premium plan, which is for 59,999. Okay. So in the premium plan, we also have personalized guidance on the notes. So if you want, you can avail any of the three plans as per your convenience and needs. Plus, you can get additional 20% discount by using my promo code as displayed on the bottom of the screen. Okay, so with this, let's begin our class for today, that is enzymes. So firstly, describing that what are enzymes. So enzymes are protein catalysts that increase the rate of a reaction without being changed in the overall process. So most of your enzymes, they are proteins. Not all enzymes are proteins, but majority of enzymes, they are proteinaceous in nature. Example, an exception to this are your RNA enzymes, okay? So they are not proteins in nature. So that is an exception. But majority of your enzymes, they are protein catalysts that increase the rate of the reaction. Okay, so they increase the rate at which equilibrium is attained or achieved without themselves being changed in the overall process. Okay, the word enzyme, it was coined by Frederick Kuhne. Now, what is substrate? It is that substance on which the enzyme is going to act, and product is a substance that is produced by the enzyme action. So, enzyme is going to act on a substance which is known as substrate, and as a result of the enzyme action, the substrate is going to be converted into a product. Okay. Now, see here, this is an enzyme. This enzyme is having active sites. Okay. What is an active site? It is that site of the enzyme where the substrate is going to bind. Okay, here in yellow, you can see this is your substrate. So your substrate is going to bind to the active site of the enzyme. It is not going to bind anywhere in the enzyme. Okay, your substrate only binds to the active site on the enzyme. Okay, and forms an enzyme substrate complex. And then the enzyme is going to do the catalysis, and as a result of which your products are formed. Okay, now let's talk about the different components of enzymes. Now, your enzymes, they can either be simple enzymes or complex or conjugated enzymes. So, complex enzymes are also known as conjugated. Now, what are simple enzymes? They have only protein part. So, if an enzyme it is only having a protein part, it is known as a simple enzyme. But usually what happens, your enzymes, they are conjugated or complex enzymes. So apart from having a protein part, they also have a non-protein part. Okay. So in the absence of that non-protein part, they're inactive. Okay. So they're going to be active only in the presence of that non-protein part. So let's talk about complex enzymes. So your complex enzyme, like I said, it has a protein part which is known as apoenzyme and a non-protein part which is known as cofactor or coenzyme. So if I put this in a tabular form, so I'm saying this is your enzyme. Okay, and enzymes, they have two parts. They have two types basically. Either they're going to be simple, that is only having protein part, only protein part, or they're going to be complex enzymes. Now, what are complex enzymes? These are those enzymes which have a protein part, which is known as apoenzyme, and a non-protein part. Now, this non-protein part, it can either be metal ions, that is cofactors. So your metal ions like your zinc, iron, okay, or it can be coenzymes. What are coenzymes? These are small organic compounds or molecules. So small organic compounds. Okay. So to the protein part, you have a non-protein part. Now this non-protein part, it can either be metal ions known as cofactors, or it can be coenzymes, that is small organic molecules. Okay. Usually your vitamins. Now, it can again be, your coenzymes can again be of two types. That is prosthetic group and co-substrate. Okay, so your prosthetic group, they are tightly bound to the enzyme, and your co-substrate, they are loosely and transiently bound to the enzyme. And the most common prosthetic group, they are metals. Okay, so that was in tabular form. Let's read what the notes have to say. So your cofactor, if the non-protein moiety is a metal such as zinc and iron, like I told you. So if they're metal, it is known as cofactors. Now talking about coenzymes, if the non-protein part is a small organic molecule, usually your vitamins, coenzymes are commonly derived from vitamins. Okay. But others, like your lipoic acid, it is also a coenzyme, but it is not a vitamin. So not like only vitamins are not coenzymes. You have other coenzymes as well, but most commonly they are derived from vitamins. Like your NAD plus, it contains niacin. Your FAD, it contains riboflavin. Okay, so these are all examples of coenzyme. Now coenzymes, as I said, they can either be co-substrates or prosthetic groups. So your co-substrate, there are those coenzymes that only transiently associate with the enzyme. They dissociate from the enzyme in an altered state. For example, your NAD plus. Okay. So these are your co-substrates. That is, they are not permanently attached to the enzyme. They only for some time transiently associate with the enzyme and then dissociate from the enzyme in an altered state. And what are prosthetic groups? If the coenzyme is permanently associated with the enzyme and returns to its original form, it is known as prosthetic group, like your FAD. Your FAD and FMN, we know that they are tightly bound to the enzymes as flavoproteins. Okay, so your prosthetic groups, they are tightly and permanently associated with the enzyme. Now, what is a holoenzyme? Your apoenzyme, that is the protein part, plus the non-protein part of the enzyme together, that makes the holoenzyme. And this is in its holoenzyme form, your enzyme is going to be active. Okay, so that was the general enzymology. Now let's talk about the mechanism of action of enzymes. Another very important topic, and we've already seen how many times it has been asked. So the mechanism of enzyme action has been explained by different theories. The first one being lowering of activation energy, then Michaelis-Menten theory, Fischer's-Tempel theory, Koshland's induced fit theory. So let's have a look at each of the theories one by one. So the first is lowering of activation energy. So there is a particular transition state where the reacting substance has to reach to be converted into product. So your reactants, that is your substrate, and they're having a certain amount of energy. That is the initial energy of your reactants of the substrate. Now they have to reach a particular transition state for them to be converted into products. Now, what is this transition state? This transition state is the intermediary state of the reaction. Intermediary state of reaction when when the molecule is neither a product or a substrate. It is an unstable state and, well, change into product soon. Okay, and it is the point of highest free energy. So what happens is your reactants, they're having a certain energy. They have to reach a state known as transition state. That is the point of highest free energy, and then they'll be converted into products. Now, the amount of energy that is required for the reacting substance, that is your substrate, to reach that transition state, that is called the activation energy. As you can see here in this diagram, this is the initial state of the reactants. This is the free energy of the reactants. Okay, here. This is the free energy of the reactants, and this is the transition state. Okay, now for the reactants, from here to reach here to this transition state, this energy, this is known as the activation energy. So what is the activation energy? It is the amount of energy that is required for a reacting substance to reach the transition state. Okay, now this is the transition energy. Now what happens in an uncatalyzed reaction? What is happening? Reaching the transition state is very difficult. So the enzymes lower this transition state so that the reacting substance can easily reach the transition state and be converted into products. This is known as lowering of activation energy. Again, have a look at this diagram. What happens? This is an uncatalyzed reaction. So in this was the activation energy. Now what happens by using an enzyme? What happens? You can see the transition state has been, here is the transition state. So you can see the transition state has been lowered over to, in other words, the activation energy has been lowered. Okay, so now this was the initial state of the reactants. Now this is the transition state is here. So the activation energy, this one is the activation energy in an enzyme catalyzed reaction. So you see the one in red, that is more, and the one in green, that is less. So in an uncatalyzed reaction, the activation energy was more. Now compared to a catalyzed reaction, the activation energy has been lowered. So this has been done by the enzyme. So what are enzymes doing? They're lowering the activation energy, or in other words, you can say they're facilitating the formation of the transition state. Okay. Now the question arises that where does this energy that is required to lower the activation energy comes from? Okay, so this is coming from the binding energy. Now what is binding energy? That is the free energy that is released as a result of interaction between the enzymes and the substrate. You know that the enzyme in the first PPT that I discussed, your enzyme, it had an active site. The substrate was interacting with the enzyme in the active site. So as a result of those interactions of the substrate with the enzyme in the active site, what was happening? Some free energy was being released, and that was the binding energy. So that binding energy that is used in lowering the activation energy. So the energy that is required for lowering this activation energy is coming from the binding energy. So what happens? In an uncatalyzed reaction, the activation energy was more, so less of the reactants were able to cross that transition state. But by using an enzyme, the activation energy has been lowered, so more of the enzyme, more of the substrate now will be able to cross the transition state and turn into product. But free energy remains same both in catalyzed and uncatalyzed reactions. So always remember that enzymes, they only increase the rate of the reaction by lowering the activation energy, but they do not change the free energy. Okay, that is going to remain same both in catalyzed and uncatalyzed reaction. Your enzymes, they only change the rate at which the equilibrium is attained or achieved, but they do not change the equilibrium state. Okay, you can see this was the initial state of the reactants. This was the final state of the reactants, that is products. And this is the free energy of the reaction. So the free energy of the reaction, this is same both in catalyzed and uncatalyzed reactions. So always remember that enzymes only increase rate of a reaction by lowering the activation energy, but they do not change the equilibrium state or do not change the free energy of the reaction. They only change the rate at which equilibrium is achieved. So this is the mechanism of activation or lowering of activation energy. I hope it's clear. Now moving forward to Michaelis-Menten theory. So according to this theory, the enzyme combines with the substrate to form an enzyme-substrate complex, which immediately breaks down to enzyme end product. So you can see this is your enzyme shown in yellow, which is having active sites, and this is your substrate. So what is going to happen? An enzyme substrate complex is formed. Then the enzyme acts. As a result of the action of the enzyme, products are formed. So this is your enzyme product complex, and then the products are released from the enzyme. So this is Michaelis-Menten theory, which states that your enzymes, they combine with the substrate to form an enzyme substrate complex, which immediately changes into product and enzyme. Now we have the Fisher's template theory. So according to Fisher's template theory, the active site of the enzyme is complementary to the substrate. So in this theory, it is talking about the complementarity between the active site and the substrate. That is the active site of the enzyme. It is complementary to the substrate. Thus, the enzyme and substrate, they fit each other perfectly, just like a lock and key. Okay, so that for every specific lock, you have a specific key. You cannot open any lock by any key. Okay, so there has to be a particular key for a particular lock. Similarly, there is a particular enzyme with a particular active site to which only a specific or a particular substrate is going to bind. So your active site is complementary to the substrate. But this theory failed to explain the flexibility shown by the enzyme. So this is the reason why this theory was discarded, because it failed to explain the flexible nature of the enzymes. You can see here, this substrate is having this specific shape, and the active site of the enzyme, you can see, is having an exact complementary shape to that substrate. Okay, so the active site is complementary to the substrate so that the substrate can fit into the active site. But here you can see the substrate and the enzyme, they are not complementary to each other, so the substrate will not be able to fit the enzyme's active site. Or you can see this is an enzyme. It has an active site of this shape. So a substrate which is of this shape will not be able to fit into this en enzyme's active site. So this is what the Fisher's template theory says, that the active site has to be complementary to the substrate. So this substrate can only fit in this active site and not in this active site. Okay, just like a lock and key. Therefore, this theory is also known by the name of lock and key theory. Now moving on to Postlan's induced fit theory. According to this theory, initially the substrate binds to a specific part of the enzyme. This leads to substrate-induced conformational changes in the active site of the enzyme to fit the substrate into it. Just like a pair of gloves take the shape of the hands of whosoever wears it. This theory can also explain the dynamic changes associated with enzyme action. So here in this theory, it says that your substrate is going to bind to a specific part of the enzyme, and because of this binding, what will happen, there is going to be conformational change. The substrate binding is going to induce conformational changes in the active site, and now the active site is going to become complementary to the substrate, and the substrate will be able to fit into that. Just like you wear a pair of gloves. Okay, so anybody who's going to wear the gloves are going to take the shape of person, take the shape of the hands of the person who's going to wear it. Okay. So similarly, you can see here the active site is not complementary to the substrate, but because of the binding, what happens? The active site becomes complementary, and then it is changed into products, and then you can see the enzymes in the products, they are released. Okay. So this theory was accepted because it was able to explain the dynamic changes associated with the enzymes. So we all know enzymes, according to this theory, it stated that enzymes are flexible and shape of active site can be modified by binding or substrate. Okay, so we've spoken about the mechanism of enzyme action. Now let's move on to enzyme kinetics. Very important, very frequently asked. So let's talk about enzyme kinetics. Firstly, talking about factors affecting enzyme activity. Okay, so let's talk about the enzyme concentration. The reaction velocity is directly proportional to the enzyme concentration, provided that the substrate concentration is constant, and this gives a straight line graph. Okay, so they are trying to say that the velocity of a reaction is directly proportional to the enzyme concentration. So as you increase the enzyme concentration, the velocity of the reaction is going to increase, provided your substrate concentration is constant. So if you're not increasing the substrate and you're increasing the enzyme, then more of the substrate is going to bind to the enzyme. So the reaction velocity is going to increase. So therefore, if the substrate concentration is kept constant, so on increasing the enzyme concentration, your velocity is going to increase. So this is going to give a straight line graph. Okay. So that is how your reaction velocity depends upon enzyme concentration. Now talking about temperature. So there are two ways of increasing the reaction velocity. Okay. First is by increasing the temperature. If you increase the temperature, the kinetic energy of the molecule is going to increase, and more of the reactants are going to cross the activation energy barrier and turn into products. The other way is that you use a catalyst. Now here also your enzymes are working within a very narrow range of temperature and pH. What happens on increasing the temperature? The reaction velocity is going to increase, because what happens when you're using an enzyme? So if the enzyme catalysis, as we've already mentioned, is based on the collision between the reactions in the enzymes. Okay, so they have to form an enzyme substrate complex. So when you increase the temperature, the kinetic energy of the reactant is going to increase. So more of the substrate is going to collide with your enzymes. But now here there's something very tricky. Since your enzymes, they are protein in nature, if you increase the temperature too much, what will happen? They will get denatured. Okay. Now let's read what the notes have to say. Initially, on increasing the temperature, the reaction velocity increases, reaches a point of maximum velocity at optimum temperature. Then there is a drastic fall in the velocity, which is due to denaturation of enzymes. Okay, so what is happening? You're increasing the temperature. The velocity, the kinetic energy possessed by the reactants, that is going to increase. Okay, more of collisions are going to take place between the enzyme and your reactants. Okay, and more if product is going to be formed. So as you increase the temperature, the reactions velocity is going to increase until it reaches a maximum point. Okay, that is where the your reaction velocity is maximum, and this is the optimum temperature for a given enzyme. Okay, now what happens beyond an optimum temperature? If you still continue to increase the temperature, what is going to happen? There's going to be a drastic fall in the velocity of the reaction. And why is this happening? Because of denaturation of the enzymes. As your enzymes, they are proteins, and proteins, we all know, they get denatured at high temperatures. Okay, so this is going to give a bell-shaped curve. So why do we say it's going to give a bell-shaped curve? Because as I mentioned, the enzymes are working in a very narrow range of temperature and pH. Okay. So there is this optimum temperature, that is where you have the maximum velocity of the reaction, and beyond this optimum temperature, either below or above this optimum temperature, your reaction velocity is going to decrease. Okay. So therefore, you're going to get a bell-shaped curve. You can see here, this is the optimum temperature range, and in this optimum temperature you are getting maximum velocity. But as you go below or above this temperature, what happens? Your reaction velocity is going to decrease. And what is optimum temperature? It is that temperature at which you have the maximum velocity. Now, optimum temperature of most enzymes in our body is between 35 to 40 degrees Celsius. What is Q10? For every 10-degree rise in temperature, the reaction velocity doubles. That's Q10. Now, this optimum temperature, it varies greatly from enzyme to enzyme and organism to organism. Like I said, for most enzymes in a body, the optimum temperature is 35 to 40 degrees Celsius. But for Taq DNA polymerase, Taq DNA polymerase, you will study about this when we study PCR. For this, the optimum temperature is 72 degrees Celsius. So the optimum temperature, it varies greatly depending upon the enzyme, depending upon the organism. This Taq polymerase, DNA polymerase, it is found as Thermus aquatis, which is found in hot springs. Now talking about the pH, again a bell-shaped curve is shown, very similar to the effects of temperature. That is on, there's an optimum pH where the enzyme is going to have maximum velocity, and beyond that is above or below that optimum pH, the reaction velocity is going to decrease. So the optimum pH is the pH at which there is maximum velocity. In our body, the optimum pH is between 5 to 9 for most enzymes. In the stomach, the optimum pH is in the acidic range, that is 2 to 4, and in the intestine, the optimum pH is in alkaline range. Thus, intestinal enzymes, they will not work in the stomach, and the stomach enzymes, they will not work in the intestine, because the enzymes are going to work in their optimum pH range only. Okay. So you can see there is a bell-shaped curve. At the optimum pH, you have maximum velocity, and below the or above the optimum pH, the velocity is going to decrease. Okay. Now, why do you think the activity on the enzyme is going to depend on pH? Let's talk about that. So the active sites of the enzyme, active sites of enzyme. Active site is the site where your substrate is going to bind to the enzyme. Okay, so the active sites of enzymes, they have charged amino acids. Now, if there is a variation in the pH is going to change. So we all know that due to change in the pH, the charge on the amino acid is going to change. So variation in pH changes the charge of amino acids, and as a result of which the catalytic activity is going to be affected, okay, which depends on the specific state of ionization of the amino acids. So the charge on the amino acid is going to change, so the catalytic activity of the enzyme is going to change. That is how the activity of the enzyme is dependent upon pH. And this is why your pH becomes important, because on changing the pH, the charge of the amino acids in the active site of the enzyme, that is going to change. And as the charge changes, the catalytic activity is going to be affected, because your catalytic activity depends upon a specific state of ionization of the amino acids. Now talking about substrate concentration. So it gives a hyperbolic graph on keeping the enzyme concentration constant. Initially, on adding the substrate, the reaction velocity increases. That is, your velocity is directly proportional to substrate concentration. So your reaction velocity increases on increasing the substrate concentration, provided the enzyme concentration is kept constant. but later on reaches a plateau phase as there is saturation of the enzyme with the substrate after the initial phase, which is known as substrate saturation curve. So the initial phase is following first order kinetics where your reaction velocity is directly proportional to the substrate concentration. And then in the plateau phase, it is following zero order kinetics. That is, your reaction velocity is not going to depend upon the substrate concentration. Let's have a look at the graph. It is a hyperbolic graph, as you can see here. Initially, what is happening? As you increase the substrate concentration, the reaction velocity is decreasing. That is, your reaction velocity is directly proportional to substrate concentration. So here in this part of the graph, this is following first order kinetics. But after a certain point, after reaching the maximum velocity, what happens? Your reaction velocity is not going to depend on substrate concentration. It is going to reach a plateau phase. Okay. And here it is following a zero order kinetics. Okay. Now, no matter how much substrate concentration you increase, the maximum velocity or the reaction velocity of the reaction, it is going to remain unchanged. It is not going to depend upon the substrate concentration. Why? Because the saturation state has been attained. Okay. Initially, what happened? You had a certain amount of enzyme and you had certain amount of substrate. So it's few of the enzymes were bound with substrate. Okay. If I show this graphically, then maybe you'll be able to understand. Okay, so these black dots, these are representing your substrate. An enzyme I'm showing in red like this. This is enzyme. Okay. So the enzyme concentration is kept constant. So let's suppose you have 6 enzymes. So initially what happened? 2 enzymes were bound with substrate. Okay, you can see here. Now you increase the substrate concentration. Now on increasing the substrate concentration, 5 enzymes were bound with your substrate. So on increasing the substrate concentration, your reaction velocity is going to increase. Now what happens on increasing the substrate concentration to such a level that all your enzymes, free enzymes, they're already bound or saturated with substrate. So your all the free enzymes they have converted into enzyme substrate complex. Okay, so now there are no free enzymes to bind to substrate. So this is the substrate saturation point has been reached, and this is where your plateau phase occurs. Now, no matter how much substrate concentration I increase, since the enzyme concentration is same, all the enzymes are already bound with substrate. So on increasing the substrate concentration, the velocity is not going to increase. Okay, because all the free enzymes are already converted into enzyme substrate complex. I hope it's clear now. Okay, so this is what is meant by substrate saturation curve. Okay, and here in this phase, it is going to follow zero order kinetics. Now let's talk about Michaelis-Menten constant, very important. Okay, so I'm going to write an equation. We know that is the reaction velocity of a reaction is equal to V max multiplied by the substrate concentration divided by Km plus substrate concentration. Okay. Now this equation, this is the basic equation of enzyme kinetics. Which is known as Michaelis-Menten equation. Now, how this equation has been derived, you don't have to go into the chemistry and mathematics of all that. Just know that this is the basic equation of enzyme kinetics. It has been derived using a lot of assumptions, and this is known as the Michaelis-Menten equation. Okay. Now, considering a scenario where the substrate concentration is equal to Km. Okay, so if your S is equal to Km, then V max, so S is equal to Km. So here in place of S, you can write Km, okay, and Km plus Km. So what will you get? You will get V max is equal to Km upon V, Km plus Km is 2 Km. Now 2 km will cancel out. So you get V naught is equal to V max divided by 2. So this is, I haven't done anything, but this is like very simple maths. If we consider substrate concentration is equal to Km and you replace the substrate concentration here with Km, and then when you solve this, you get this. That is your velocity of the reaction is half of V max. So what is Km? It is that substrate concentration where the velocity of the reaction is half of maximum velocity. That is your Km. This is exactly what it says. It is that substrate concentration at which velocity of the reaction is half of maximum. Okay, and how I just derived it, this has been derived from Michaelis-Menten equation. Okay, now this Km is a constant for a given enzyme substrate pair. Okay, this is like a thumb impression or a signature of an enzyme. Okay, so your Km value is constant for a particular enzyme and it tells you about the affinity of a substrate towards the enzyme. That is, higher the Km, lower is the affinity of the substrate for the enzyme, and lower the Km means higher is the affinity of the substrate for the enzyme. What is Km? Km is substrate concentration. Okay, now if you need a lot of substrate to attain the half of Vmax, that means you're having higher Km, you're needing a lot of substrate, therefore it implies that the affinity of the substrate for the enzyme should be low. Okay, that is why you're needing a lot of substrate. Okay, so higher Km, that is when you're needing a lot of substrate concentration, implies that the affinity between the enzyme and the substrate is low. Whereas what we lower Km means you need a little amount of substrate concentration and you will be able to achieve half of the maximum velocity. That means the affinity between the substrate and the enzyme is too good or it is high. So lower Km means the affinity between the substrate and the enzyme is good, and higher Km means that the affinity between the substrate and the enzyme is low. So the Km value helps to find out ideal substrate for every enzyme. Okay, so your different enzymes that act on the same substrate have different Km values. Okay, different enzymes that act on same substrate have different Km values. So if an enzyme that is acting on a substrate is having a lower Km, means it is having a good affinity. So we can find out that this must be the substrate for this enzyme. Okay, so by using the Km value, you are able to find out which is the ideal substrate for a given enzyme. Because the same enzymes, different enzymes acting on the same substrate will have different Km values. Okay, and now let's talk about what is Lineweaver-Burk double reciprocal plot. So here, this Michaelis-Menten equation that we've had, this gives a rectangular hyperbola. Okay, if you plot V naught, that is reaction velocity against substrate concentration here. Okay, this reaction velocity against substrate concentration. So you're going to get a rectangular hyperbola. Now the maximum velocity, it is going to be attained asymptomatically. Okay, the maximum velocity is being approached asymptomatically. So therefore, to overcome these difficulties, your Michaelis-Menten equation can be rearranged to give convenient graphical representations. Because you can see here, if you're using this Michaelis-Menten equation to plot a graph, you're getting a rectangular hyperbola. And this in this rectangular hyperbola, you can see that your Vmax is being approached asymptomatically. Okay, for determining Km using substrate saturation curve is not very accurate since Vmax is approached asymptomatically. That is, it is going to meet somewhere at infinity. Now, how will you be able to find out Km from this? Okay, so to overcome these difficulties, we are going to rearrange that Michaelis-Menten equation that I mentioned above to give a more convenient graphical representation. Okay, so your V naught is equal to V max into substrate concentration upon Km plus substrate concentration. This was a Michaelis-Menten equation. Okay. Now we're going to take the reciprocal of this equation. That is, you invert it. Okay. So V naught will become 1 upon V naught and the denominator will go in the numerator and the numerator will go in the denominator. Very simple maths. Okay, we've just reversed it, taking the reciprocal. That is what we say. Now, 1 upon V naught is equal to, now you are adding Km to S. Okay, again, some simple maths going to be done here. So this is the common denominator. Okay, so we can also, I'm just writing this in a different way. Okay, so if you had attended your maths class, you will not be confused right now. Okay, this here is nothing but same as this. Okay, I've written the same thing in a different manner. Okay, here if you take, now if you add these two, you can take this as a common denominator and write it in this way. So I've just separated the two. Okay, now you what happens, this is S and S, you can cancel this out. Now you end up with, you just multiplying it by S. Okay, plus 1 upon V max. Now this that you're ending up with here, I'm sure this must be reminding you of something. The equation for straight line graph, that is y is equal to mx plus c, where m was the slope and c was the y-intercept. This is the equation for a straight line graph. So if you plot y against x, that is 1 upon v naught versus a graph of 1 upon s. Okay, so this is exactly what it is, 1 upon v naught versus 1 upon s. If you plot this graph, you get a straight line where the slope is, you've just taken out the slope is km by v max here. This is the slope, so you can see the slope is km by V max, and this is the y-intercept, that is 1 upon V max. Okay, so we've just rearranged your Michaelis-Menten equation, taken a reciprocal so that we get a straight line graph and we're able to find values more easily using this graph. Okay, so this graph here is known as Line-Weaver-Burk double reciprocal plot. Okay, so for determining the Km values using a substrate saturation curve was not very accurate, as we've just seen that it was a rectangular hyperbola and the Vmax was being approached asymptomatically. Now instead a plot of reciprocal of velocity versus reciprocal of substrate. So we've just seen that how it was derived is taken, which gives a straight line and is used, which is known as Line-Weaver-Burk double reciprocal plot. It is much easier to calculate Km using this plot. This plot is also very useful in understanding the effect of various inhibitions. So now moving on to enzyme inhibition. So you will see why this plot is very important. So now let's talk about enzyme inhibition. So enzyme inhibition is classified into competitive, non-competitive, uncompetitive, site inhibition, feedback inhibition, and allosteric inhibition, all of which is very important. So let's talk about competitive inhibition first. So here the inhibitor and the substrate, they are structural analogues of each other. They're going to be more or less similar in structure. The inhibitor binds to the same site where the substrate is going to bind. That is, your inhibitor is going to bind with the active site. You can see this is your enzyme and it binds with the substrate, it forms enzyme substrate complex. But instead, if an inhibitor binds, it is going to bind enzyme inhibitor complex and no product is going to be formed. Okay, but this is an example of reversible inhibition. Inhibition can be overcome by increasing the substrate concentration. So if you increase the substrate concentration, more substrate will get a chance to bind to the enzyme and this inhibition can be overcome. So your Km is going to increase because you're increasing the substrate concentration, but Vmax is going to remain constant. Okay. So you can see here, Vmax is remaining constant, but your Km increases. So the Km has shifted. Again, here also, your Vmax, you can see it is remaining the same, but your Km has increased. So this is your Km now. Now, examples of competitive inhibition. They are drugs commonly used for competitive inhibition. For example, your statins, it inhibits HMG-CoA reductase. It is a structural analog of HMG-CoA. So, HMG-CoA reductase was involved in cholesterol synthesis. So, for someone who's having high cholesterol, your statins are given since they're going to inhibit HMG-CoA reductase. So, your cholesterol will not be synthesized anymore. Dicomerol, it inhibits vitamin K epoxide reductase enzyme. Your methotrexate inhibits dihydrofluorate reductase, and your succinyl-CoA, it inhibits acetylcholine esterase. We're talking about non-competitive inhibition. The enzyme has an active site to which the substrate is going to bind, and the inhibitor binds to another site which is not the active site. So unlike competitive inhibition where your inhibitor and the substrate, they were both binding to the same active site, here the inhibitor is going to bind to another site. You can see here in the diagram, there is this another site where the inhibitor is going to bind and the substrate is going to bind to the active site. So the substrate and the inhibitor, they are not structural analogs. As you can see here, both of them, they're not structural analogs of each other. Now here the Vmax decreases and Km remains same as the inhibitor does not interfere with the enzyme substrate binding. So the substrate is going to bind to the enzyme in the manner in which it was binding. Okay. But the substrate will bind to the active site. But what will happen because of the presence of the inhibitor in the other side, product will not be formed. And here your Vmax is decreasing and Km remains same. You can see your Vmax is decreasing, but Km is remaining same. Similarly here, your Vmax decreases and Km remains same. The inhibitor can bind to the enzyme as well as the enzyme substrate complex. So the inhibitor is binding not just to the free enzyme, but also to the enzyme substrate complex. Either way, what is happening, the product is not going to be formed. So most of the non-competitive inhibitors are irreversible except for the action of trypsin inhibitor on trypsin. Now, some of the examples of non-competitive inhibitors, most of them are poisons. Okay. Your cytochrome C oxidase, it is inhibited by cyanide. That is one example. Glyceraldehyde 3-phosphate inhibited by iodoacetate. We've studied this in glycolysis. Enolose inhibited by fluoride. Again, we've studied this in glycolysis. Alpha ketoglutarate dehydrogenase is inhibited by arsenite. We've studied this in TCM. Aconitase, it is inhibited by fluoroacetate. Again, we've studied this in TCA. Then talking about uncompetitive inhibition. So inhibitor does not have any affinity for free enzyme. Now this is the difference between non-competitive and uncompetitive. In non-competitive, your inhibitor, it was binding both to the free enzyme and the enzyme substrate complex. But here, the inhibitor can only bind to enzyme substrate complex and not to the free enzyme. The Vmax is decreasing and Km is also decreasing, where the Km was remaining same because your inhibitor was not interfering between the substrate and the enzyme interaction. The inhibition of placental alkaline phosphatase by phenylalanine. This is the example of uncompetitive inhibition. Now talking about suicide inhibition, it is also known as mechanism-based inhibition. Here what is happening, the original inactive inhibitor, which is a structural analog, gets converted into a potent inhibitor by using the enzyme's own reaction mechanism and inactivates it. So basically what is happening initially, the inhibitor, so the original inhibitor, it was inactive, okay? So the original inactive inhibitor, it is going to bind to the enzyme as a substrate because it is yet inactive. Okay, now what happens? And is initially processed by the normal catalytic mechanism. So your inactive original inhibitor, it is going to bind to the enzyme just like a substrate binds, and then it is going to be processed by the normal catalytic mechanism of the enzyme. Okay. As a result of this catalysis, now what is going to happen? So as a result of this catalysis, after being processed by the enzyme's own mechanism, okay, what is going to happen? This substrate or this inhibitor, which was inactive, this inactive inhibitor, it is going to be converted into a reactive intermediate that inactivates the enzyme. Okay, just like suicide, literally. Okay, so this is what is happening in suicide inhibition. So the your initial inactive inhibitor, which was also a structural analog, so it was going to act as a substrate. It binds to the enzyme, and then because of the enzyme catalysis, what is going to happen? It is going to be converted into a potent inhibitor. It forms a reactive intermediate, which is going to inactivate the enzyme. Okay, so this newly formed potent inhibitor binds irreversibly to the enzyme. This is a special type of irreversible inhibition. So your suicide inhibition, therefore, it is also known as mechanism-based inhibition. Now, examples are your allopurinol inhibiting xanthine oxidase. So we all know allopurinol, it is given in the treatment of gout, where you want to decrease the uric acid levels. So you inhibit xanthine oxidase. But your allopurinol, it binds to xanthine oxidase and it's converted into alloxanthine, which irreversibly binds the enzyme xanthine oxidase. And another example being difluoromethyl ornithine, which inhibits ornithine decarboxylase. Now talking about feedback inhibition, the end product inhibits the first enzyme. It is known as end product inhibition. So for example, you have a substrate A which forms B, then this B forms C, and then C forms D. So your D is the end product, and this is brought about by various enzymes E1, E2, E3. Now what happens? This end product D that this is which is formed, it is going to inhibit your A. So this is known as end product inhibition. Okay, an example be, for example, you increase mevalonate, it inhibits HMG-CoA reductase. So your HMG-CoA, it is forming mevalonate, and the enzyme is HMG-CoA reductase. So if you have increased mevalonate, it is going to inhibit this HMG-CoA reductase. So this is your example of end product inhibition. Now what is end product regulation? Here what is happening? The end product is not acting on the enzyme. Instead, the end product will inhibit the gene that transcribe and translate the enzyme one. So here what was happening? Your end product, it was inhibiting the first enzyme. That is in feedback inhibition or end product inhibition. But in feedback regulation, what is going to happen? Your end product, it is going to inhibit the gene which is going to transcribe that first enzyme. For example, if there is enough of dietary cholesterol, then this decreases binding of SREBP at genes that synthesize HMG-CoA reductase. So your HMG-CoA reductase gene is going to be inhibited. That is feedback regulation, leading to decreased expression of the gene that synthesizes HMG-CoA reductase. Okay, so that was about different types of inhibition. Now we're only left with allosteric inhibition. So you can regulate the enzyme activity in two different ways. That is either by regulating the quantity of the enzyme produced or the quality, or that is its catalytic activity. Okay, so in quantity, you can control the quantity of the enzyme synthesized. That is either by induction or repression. Okay, so you either induce or suppress the structural genes with the help of inducer and repressors, and therefore you control the quality of the quantity of the enzyme synthesized. Okay, so with the help of an inducer or repressor, the structural genes for a particular enzyme can be inhibited or stimulated, thus controlling the synthesis of that enzyme. For example, your ALA synthase. Okay, so if the level of heme in the body is low, what is going to happen? The structural genes for ALA synthase, they're going to be active, and more ALA synthase will be produced, leading to more heme synthesis. So this is how you're controlling the quantity of the enzyme synthesized. You're either increasing the quantity of the enzyme synthesized or decreasing. Or the other way is that you're controlling the quality or the catalytic activity. That is, the enzyme is there, but you're either activating or deactivating it. So that comes under two types of regulation: allosteric regulation and covalent modification. That is, how are you controlling the quality or the catalytic activity of the enzyme. So talking about allosteric regulation, allosteric enzyme is an enzyme whose activity in the catalytic site is modified by the presence or absence of a modifier in allosteric sites. So your allosteric enzymes, they are having a catalytic site as well as an allosteric site. So in the allosteric site, a modifier is going to be present, and depending upon the kind of modifier that is present in the allosteric site, the enzyme's activity is going to be decided. Okay, so if the modifier present is an activator, the activity is going to be enhanced. If the modifier present in the allosteric site is an inhibitor, the enzyme is going to be inhibited. Okay, so such enzymes can act only if the modifier is present. Allosteric enzymes have two sites: catalytic site where the substrate binds, and allosteric sites where the modifier binds. If the modifier is an activator, enzyme will be active. If the modifier is an inhibitor, enzyme will be inactive. And depending upon the modifier, two types of allosteric regulations are the allosteric activation and allosteric inhibition. It's very simple. I'll repeat it. Your allosteric enzyme, it is having, let's suppose this is the allosteric site where your modifier is going to bind. Now this modifier, it can either be an activator or an inhibitor. If it is an activator, the enzyme is going to be active. It is an inhibitor, the enzyme is going to be inactive. Okay. And there's another catalytic site where the substrate is going to bind. And for this allosteric enzyme to function, the modifier has to be there. Okay. Now talking about allosteric activation, the catalytic site is not favorable for the substrate to bind. But because of the modifier, if it is an activator, what is going to happen? When it binds to the allosteric site, the unfavorable catalytic site is converted into a favorable catalytic site for substrate binding. So you can have a look at this diagram here. This is the active site. And this active site, as you can see, it is not favorable for the substrate to bind. But what happens when a modifier is going to bind to the allosteric site? It is going to bring about conformational changes in the active site and make the active site suitable or complementary for the substrate to bind, favorable for the substrate to bind. So this is known as allosteric activation. Now, what is allosteric inhibition? When a modifier, which is an inhibitor, binds to the allosteric site, it is going to make this favorable active site not so favorable for the substrate to bind, and you can see this is going to lead to allosteric inhibition. So in allosteric inhibition, when the modifier, which is an inhibitor, binds to the allosteric site, the active site is going to become unfavorable for substrate binding, and the reverse is going to happen in allosteric activation. Okay. Now moving on to the characteristics of allosteric regulation. So most allosteric enzymes, they are multiple subunit enzymes possessing quaternary structures. So they're having multiple subunits. Basically, they are having catalytic units and regulatory units. Okay, so the regulatory units, you have allosteric sites where your modifiers are going to bind. Now, homotrophic effectors, when the substrate itself serves as an effector. Usually substrate functions as positive effector. So what is homotrophic effect? Here, the substrate itself is going to act as a modifier or as an effector. So when substrates, they are acting as effectors, they are usually acting as positive effectors. And as a result of which, what is going to happen? Binding of substrate to one of the subunits of the enzyme may enhance binding substrate at the other subunits. This is known as positive cooperativity. So what is happening, as we mentioned, that your allosteric enzymes are having multiple subunits. Okay, so what happens, because of the binding of the substrate at one of the sites, the binding of the substrate to the other sites is going to be enhanced. This is known as positive cooperativity or homotrophic effect. That is, your substrate is the same, or your modifier is the same as the substrate. Okay, so in other words, you can say your substrate itself is acting as an effector. That is homotrophic effect. Now, what is heterotrophic effect? The effector is different from the substrate. When the inhibitor binds to one side, which will inhibit binding of substrate to other sides. This is known as negative cooperativity. So, your inhibitor is going to bind at one side, and as a result of which, your substrate will not be able to bind to the other sides. This is known as negative cooperativity. And this is heterotrophic effectors. Now, allosteric enzymes do not follow Michaelis-Menten kinetics. Instead, they give a sigmoid curve because of cooperativity. Allosteric enzymes occupy key regulatory positions in metabolic pathways and are called as key enzymes or rate limiting enzymes. So, in all the pathways that we've studied, your rate limiting enzymes, almost all of them, they are allosteric enzymes. So, now, adding allosteric activator, curve shifts to the left and Km is decreased. And on adding allosteric inhibitor, the curve shifts to the right and Km increases. Here you can see this is your sigmoid curve. And on adding a positive modifier, the curve is shifting to the left. And on adding a negative modifier, the curve is shifting to the right and the Km is decreasing. Okay. So with this, we come to the end of today's class. If you have any queries, you can ask. Thank you for watching. See you in the next class.